Okay. Good evening, everyone. So today is the fifth week of fluid flow operation class, and in this week, sir has talked about the main part of the fluid mechanics, that is the Navier-Stokes equations, the laminar flow, the turbulent flow, how the equations are solved, and the boundary layer theory. So this part is very important because you already know that in our um like in our surroundings or even in our body also, everything is fluid. Like there is air, right? It is also one kind of fluid. Or you can say it is one kind of fluid which doesn't have uh, any like viscosity or very less density, right? So this is also fluid. So we move around fluid. So we are an object in the air. That means like when we are walking, so we are object in a dimension, fluid domain. We can consider that. So in our body everything is fluid. There are micro channels, right? So there are channels in our body, lots of like lakhs of channels which are around in the range of micrometer, somewhere it is nanometer, right? So through all of them fluids are passing. Blood is flowing. Blood is a kind of fluid. So how these things are, but we are observing, or we will be studying today in macroscopic scale. That is in microscopic scale. That is little bit different, but the equations working are everywhere. It is same. So when you go on a flight, right? So the aeroplane movement, the complete aeroplane movement is based on fluid dynamics and the fluid dynamics theory, all these boundary layer theory and laminar flow, turbulent flow. So these are very important parts. So today we are going to learn, or today we are going to revise the session, whatever sir has taught again about this basic equations, like how can we define this phenomena in terms of equations. So, and we will do some derivations because these are the basic derivations which you have to do throughout your life if you want to study fluid dynamics or related things, basically chemical engineering. So this will be a very important, very basic part of chemical engineering or everyday life hour. Okay, so let's start with that. So I'm sharing my screen. So I think my screen is visible. Okay, so we'll start one by one. But at some point, I may differ from Sir, the way Sir has derived. I may differ, but the thing is, everything is like at the end, the equation will come same, and you can define or you can derive these things in many ways. So I will show you how many ways you can solve it. Okay, so that's why it may be a little bit different from what Sir has taught, but it is the same thing. So in the last class, we have learned about the Reynolds transport theorem, right? We have learned about the momentum equation. We have learned about the momentum equations, the continuity equation, the mass balance equation, how the mass conservation equation works, how the momentum conservation equation works, and how the energy conservation equation works, right? Along with that, we have learned an extra thing, which was the Reynolds transport theorem. So basically, from Reynolds transport theorem is a generalized equation of fluid dynamics, and from where you can define or you can derive the mass balance equation, the momentum balance equation, and as well as the energy balance equation. So we will start uh, from there. Like we'll use somewhere the Reynolds transport theorem. Okay. So uh, so sir has this one. Yes. Yeah. So no, this is the lecture 10. So here comes the first, like this is the basic equations we have learned last week. And now comes the Navier-Stokes equation. So how the Navier-Stokes equation will come? So here comes the derivation of Navier-Stokes equations. Okay. So what you can consider, suppose I will do the assignment also and some extra questions also. But first understand the basics. So suppose we are considering a control volume. Yeah. So that is suppose a cube. That is a cube. And we are considering in 3D control volume. So this is the 3D axis. This is your X, this is your Y direction, and this is the Z direction. Right? Okay. Now we are, so at the middle, there is a point P whose coordinate is X, Y, and Z. Right? Now suppose we are giving stress. So we have learnt about the stress. It is the tangential force. Right? Tangential force per unit area. It is in pressure. Right? So suppose we are giving stress. Okay. So we are giving stress first in the x direction. Yes. So from the middle, you can consider this half and you can consider that half. This is the plus x direction. This is the minus x direction. Okay. So in the x direction, now so in the, as it is a tensor, so in the x direction, there will be three components, right? So they are tau xx, tau yx, and tau zx, right? So from the x, so we are at this case, like this is the zy, right? So x directional stress will work on the zy plane. We are considering this is the zy plane, you know, right? So here the force is also in the x direction and the area of working force is also in the x direction, right? So here it will be tau xx plus, as we are considering, suppose from the differential point, so from middle the point is there, so we are considering from this half and that half, so the distance is dx by 2. Okay, so it will be at the middle the stress is tau xx, so in the plus half direction it will be tau xx plus del x of tau xx and dx by 2, because we are considering from the middle, right? So we are not considering from one portion, we are considering from the middle of the cube, middle point of the cube, right? So this is the plus directional stress exchange. And in the negative x direction it will be like tau xx minus del x of tau xx dx by 2, right? So this is the stress exchange in the differential distance of dx by 2 in both the cases, right? You can define it like from, if you are in the at one point, so it will be tau xs and that will be tau xx minus del x of tau xs dx, because the distance is, this distance is dx. But we are considering it from the, we are calculating it from the middle point. That is the differential finite difference method. So that is different thing. I am not going too much about FDM or what is finite difference method. But if you consider the middle part, you have to go dx by 2 direction, and this way you have to go dx by 2 direction, right? Okay. So now what will be the tau yx? So tau yx will work on this direction. This is the, so from x, the area working will be in the x direction and the force in the y direction, right? So this will work on this plane. So it will be this direction. This is the plus y direction and this is your minus y direction, right? So how it will change? So it is the, in the positive direction, tau yx plus del y of tau yx, and the change is dy by 2, right? Similarly, in the opposite direction, it will be tau yx minus del y of tau yx dy by 2, right? Right? Now for the z also this will work. So this is from the x directional perspective. So we are at this x directional perspective. That is why there are three components of x, there are three components of y. So what will be the y component? So it will be tau xy, tau yy, and tau zy, right? And for z directional it will be tau xz, tau yz, and tau zz, right? So these are the 9 components of stress. So now, like this is the x directional, this is the y, this is the x directional, this is the y directional, right? Just a minute. Okay, I have given a wrong indication. So x direction is fine. So tau xs will work on this and tau xs minus will work on this. But in case of tau yx, the force should be in the x direction because we have earlier learned that x is the force direction and y is the on which area it is working, direction of, right? So here it will be like this. So it is in the y plane. That means it is in the xz plane, but that force direction will be in the x direction. So this is the tau yx positive direction, and this case in this part it will be like the minus. So if I define it with another color, it is the tau yx plus direction, and this is the tau y x minus direction. So the force direction in the x direction, but the area on which it is working, it is in the y zone. So it is in the xz plane, right? Now you get it. Similarly for the z also, also it will be in the xy plane. So this will, but the force will be at the x direction, that is this one is the tau zx plus del del z of tau zx dz by 2, and here it will be in the bottom direction, it is in the minus direction, so it is like this. So this will be tau zx minus del del z of tau zx into dz by 2. Okay, so these are the different components of x. Now we are not writing the rest of the things because it will be very very chaotic or very clumsy image. But if you want to see here, we can show in the other page, right? So for tau yy, right? For tau yy, the direction is this and minus direction is this. Okay, this is tau yy. Next comes the tau xy. So tau xy, it will be in this direction and it will be in the opposite direction. So this is the tau xy, and what will be tau zy? Tau zy will be your, like in the z platform, it will be tau zy, and in the bottom plate it will be, this will be tau zy. Similarly for z components, another last three components of, so this is the tau zz and this is a minus tau zz, right? Next comes the in the x direction, this is the tau x set, and this is, in this portion, it is the tau yz direction, right? So these are all the similar things. I hope this is clear. The directions are clear, how the 9 components are coming, because in the each direction there are three components, because it is a tensor, right? It is not only a vector, it is a tensor. So it has, if it is a vector, then it has 3 components, but as it is a tensor, so it has 9 components, because in each 3 directions there are three components, right? I hope it is clear now. The directions part, the control volume part, how you can imagine it. Now coming to the like how this thing is changing into how the momentum balance or mass balance is completely changing into your Navier-Stokes equation, right? So we call it Navier-Stokes equations because it contains all the mass balance equation, momentum balance equations, and if required, the energy balance equations. Okay. So momentum balance equation we have seen earlier, but still in the differential approach I am going to solve it. So this is, if you imagine, this is the same control volume, the cubic control volume we are considering, and from conservation of mass, what have we got? From conservation of mass, we have seen earlier class that this is 0 and this del T of rho dV plus summation of xyz rho v dA. So if you don't remember this derivation, please go through my previous lecture that is uploaded already in the YouTube. So there it is written that how this conservation of mass is coming, right? So if you want me to show, I can again just refer. So this one. So if you remember this, right? This is a conservation of mass, and this conservation of mass means this extrinsic property n is m and eta, the intrinsic property, is 1. So how this is coming? So from Reynolds transport theorem. So this is our Reynolds transport theorem, right? This is our Reynolds transport. And now if we put all the values, so dm dt equals to 0, n equals to m and eta equals to 1, it's coming exactly like this. Del T of rho dv and rho v dA. So if we change the term with applying Leibniz theorem and Gauss divergence theorem, so it is coming like this conservation continuity equation, right? So this is your continuity equation. So still I am not doing it. If you have seen it, right? That how this is coming. So if you apply divergence theorem here, it will come as rho v dv, divergence of rho v, dv. So if you take common of dv like this, it will come as del rho del t plus divergence of rho v. So this is your continuity equation. So del rho del T plus divergence of rho V equals to 0. So this is for the continuity equation, general continuity equation, and now if you consider the incompressible flow, it will be del rho del T will be 0, and only it will be del rho divergence of rho V. So divergence of V will be 0. So this is the part of Navier-Stokes equations. Okay. Next comes the momentum equation, that how momentum equation is changing. So suppose there is a fluid particle inside a fluid. So the fluid particle will first follow this continuity equation, which we have seen how it has been derived. Now, from the conservation of mass, what we have seen, conservation of momentum, conservation of momentum or momentum conservation. From momentum conservation, we have seen that force is force definition, right? Force is the mass into like acceleration, right? So this is the total force. So total force is defined as force at the bulk force, and this is the surface force, and this is the bulk force. We have seen that already in the last class. And now force can be defined. Force can be defined simply. So it is the mass into acceleration, right? So how mass can be defined? It is the rho into, if you take the control volume cube, so this is our control volume. So this is a cube. So it has dx, dy, dz, length, width, and height. So if you multiply this, this is the volume. So rho into volume, that is rho into dx, dy, and dz, that is the dm, and this is this into ap, right? So now if we come to the individual components. So x directional component, suppose I am coming. So x directional component, okay, so x directional component, what will be? So this x component will be dfs x plus dfbx equals to rho dx dy dz, because the mass is same in every direction. So this dm will be same, but acceleration will change in apx, right? And now what is this apx? So in the last class we have learned what is the acceleration, total acceleration, right? So here we have learned what is last class or last to last class we have learned what is total acceleration, right? I am not going to that. So if you please go through those lectures. So this is the total acceleration. So total acceleration defined as del u del t, because I am considering the x directional, so it will be del u del t plus u del x plus v del u del y plus w del u del z. So this is the apx component. Okay. Next, so this is the total bulk force. So this is the expression of this bulk force, dfb. Okay, so this is the dfb component, not dfx. This is the dfbx component. Okay, so now this is a bulk force. Bulk force means like you have seen the body force basically, right? Yeah. Now comes the surface force. So exertional surface force means, just now we have seen what are the exertional surface force, that is the shear stress. So these three components, are the x directional surface force, right? So how will you define? It is again force, right? Force will be mass into force is mass in, but here we are going to represent it in terms of stress. So stress is pressure. So it will be pressure into area. So it will be, in the x direction, it will be del x of tau xx into volume dx dy dz plus del y of tau yx dx dy dz and del z of tau zx dx dy dz. Okay, this is only the x component, right? Now, if you combine this, all this force from the momentum balance equation, so you can see here. So this is the conservation of linear momentum, right? So n is p and eta equals to v. So it is coming like this. So we are going to find this component, right? Now we have component of f bx and fsx. Now we have components of fb and fs, surface force and volume force. And now we are just summing it up. So what it is coming? So from fb, it is the, so bulk force is rho dx dy dz into apx. So we are writing in the full form rho dx dy dz into apx. So apx has that big expression. So it is like del u del t plus u del u del x plus v del u del y plus w del u del z, right? So this is the total force, right? This is the total force. Okay, again I'm confusing you because it is the total force term only. It is the df basically. So df expression is like this. Okay, so this is your df, not bulk force. This is the total mass and acceleration. This is how it is represented. And this is the surface force. This is dfx. And there is another bulk force or body force, which is represented by dfbx. So this is the body force, means m into g. M is again same, rho into dx dy dz, and here g will be gx because it is the x component, right? Now we are writing like this. We are writing the momentum balance equation. So total force is F equals to surface force plus body force. So this is your total F equals to surface force is this. So this is del x of tau xx. If I take common from dx dy dz, so del y of tau yx plus del z of tau zx. If you take common of it, and dx dy dz, right? And there is another term of body force, that is rho dx dy dz into gx. So this dx dy dz is everywhere, right? So this dx, dy, dz is everywhere. The volume is everywhere. So we can cancel this term. And what it is coming? It is coming as rho into del u del t plus u del x plus v del u del y plus w del u del z equals to, this is del x of tau xx plus del y of tau yx plus del z of tau zx plus rho gx, right? This is the x directional term. Now come, similarly, if we do the y and z direction, I am not doing it explicitly. You can do it on your own. You can do it for your practice, and you should do it because it is the every line of this Navier-Stokes equation and Navier-Stokes equation derivation is important, because anywhere from anywhere the question may come, or if you want to learn more, or if you want to deep down more about like fluid dynamics area, fluid dynamics field. So every line and every equation will be very important to understand, not only to write or to remember, to understand physically the meaning of these equations, why these are written and how these are written, from where it is coming. So you have seen that this x component of Navier-Stokes equations, so this is the x component of momentum balance equation. Though this is not the final form, I will come to later. It will come later, the final form of Navier-Stokes, but it is the x component of the momentum balance equation. And this every equation and each equation is very important. So you have seen that this is nothing but the force balance we are doing in the momentum equation, right? So this is only the mass into acceleration term we are expanding like this, right? So this is very fundamental. Okay, so proceeding to the next. So this is similarly if you do on your own. So the y component will be, the y component will be, so in case of y component, what you will change to v, right? Because in x directional the velocity is u, in the y direction the velocity will be v. So it is del v del t rho into del v del t plus u del v del x plus v del v del y plus w del v del z, right? Plus equals to del x of the y components of stress, right? So what are the y components of stress? This is the y components of stress, and you have seen how they are represented here, and like means in which direction these y component stresses are working. Okay, so del x of tau xy plus del y of tau yy plus del z of tau zy plus rho gy, right? This is the y component. And next comes the z component. Similarly, you can write on your own like rho into del w del t, that is w is the z component velocity, plus u del w del x plus v del w del y plus w del w del z equals to del x of tau xz. So these are the z components, and this is how the z components of stress are working. So del x of tau xz plus del y of tau yz plus del z of tau zz plus it is the rho gz. Okay. So now if you combine all these terms, or if you want to write in vector form, what will happen? So it will be the total. So we have written rho first, right? So rho del u del t. So if you consider, so this is the del v del t combining plus v dot grad v equals to divergence of this stress tensor plus rho g. So this is the Navier-Stokes equation. Okay. So now this is the acceleration part, right? This is the local convective acceleration. This is the local acceleration. This is the local acceleration. This is the convective acceleration. So you can write this like this: rho capital dv dt equals to divergence of stress tensor plus rho g body force term. This is your final Navier-Stokes equations. Navier-Stokes equations. It is called equations because it contains all four equations: one continuity equation and three three momentum equations. Okay, so this is the Navier-Stokes equation. You can write it in the vector form also, or in indicial notation also. So I am not going into that. So now this is the generalized Navier-Stokes equation. Now if you consider, or if you want to calculate for incompressible Newtonian fluid, right? So Navier-Stokes equations for Navier-Stokes equation for incompressible Newtonian fluid. What will happen? We'll see. Why this is important? Because in our analysis, we also always consider it as incompressible fluid. Though the real fluid, none of the real fluid is incompressible, but for the analysis point of view, you have to take incompressible, otherwise the computational burden will be very high. The system will not able to solve very complicated equations, right? So that's why we take it as incompressible fluid, though it will give very good results or very good similar results to your experimental result for comparing, but none of the fluid is really incompressible or Newtonian in real world. Okay. Or if there are Newtonian fluids, like water is a Newtonian fluid, obviously, but most of the fluids are also non-Newtonian fluid. So that case you have to consider the viscosity differently. But for incompressible Newtonian fluid, we are going to solve it right now. So what is not known? So in this x component, if you see the x component, so everything is new, right? Del u del t, you know, you cannot simplify it more, but you can simplify the tau xx term, because stress from the Newton's viscosity law, Newton's law, you can express this term. So how are you express it? So if it is a Newtonian fluid or incompressible fluid, so from incompressible fluid, we can say that the continuity equation will be simply divergence of V equals to 0. This is your continuity or mass balance equations, right? In case of most momentum balance equation, what will be? So how these tau xs terms are represented? So as tau is a tensor, it has 6 components, you know. These are tau xx, tau yx, tau zx, right? Tau xy, tau yy, tau zy, tau xz, tau yz, tau zz, right? How are we going to? So there are two things. If we consider it as symmetric tensor, so we consider it as generally as symmetric tensor. Okay, symmetric tensor means except the diagonal, all the terms are same. Like tau xy is equals to tau yx, then tau zx is equals to tau xz, and tau zy is equals to tau yz. Right? This is the concept of symmetric equation. So what are the expressions? If you remember the first lecture, so this course has been started with the law of with Newton's law, Newton's viscosity law, right? So if you remember, so we have always shown that tau yx equals to tau xy. It is coming from the angular deformation case, which we have discussed in the first class, I think, in very detail. So if you have forgotten till now, please go back to that lecture. It is uploaded. All the lectures, all the previous lectures I have taught are uploaded in my YouTube channel, and which has been already shared with you in the course, in the problem solving session page, I think. So please go and see the record. So tau yx is equivalent to tau xy. That means it is the mu. So tau yx will be del u del y plus del v del x. Okay. So it comes from the overall deformation. So if time permits, I will show you how does this overall deformation is calculated, maybe in the final class or extra class, but not today. Just remember. So you have seen that tau yx is coming as individually du dy. We have proved from the from first class, right? From the Newton's law of viscosity. Next, then tau xy will be similarly mu into del v del x. So if these two are similar, so we are combining these two. This will be the overall combination, and now the summation will happen. So similarly, tau zx is equivalent to tau xz, and it is coming from, it will be mu del u del z plus del w del x. Okay, and last, tau zy equals to tau yz equals to mu del v del z plus del w del y. So these are the all other symmetric components, except that now we have come to the diagonal components. How the diagonal components are coming. So tau xx, it is defined as minus p minus 2/3 of mu into divergence of velocity plus 2 mu del u del x. So this is the expression of tau xx in general. And if you consider this is an incompressible fluid, it will lead to minus p plus 2 mu del u del x. Okay. Similarly, tau yy is expressed as minus p minus 2/3 of mu divergence of v plus 2 mu del v del y, and in case of incompressible fluid it will be minus p plus 2 mu del v del y. Similarly, tau zz will be minus p minus 2/3 of mu divergence of v plus 2 mu del w del z, and in case of incompressible fluid it is minus p plus 2 mu del w del z. Okay. Now we have got the all terms of stress component, right? So now if we just take out the stress component and see the what terms are coming, what it will be? It is the del del x of tau xx. If we are considering only the x directional stress component, del del x of tau xx, del del y of tau yx plus del del z of tau zx. How is it coming? So all the terms are coming like this, and it will be so if you so tau x is del del x of tau xx means del del x of, so we are derivating of this term, right? So I am not writing it, I am directly writing the final expression. So it will be del del x of minus p plus 2 mu del u del x. So what will be? So it will be minus del p del x, right? Minus del p del x plus 2 mu del 2u del x2, right? Now what will be that del del y of tau yx? So del del y tau yx term is mu into del u del y plus del v del x, right? So if you take the derivative of this term, what will it be? So it will be del del y of mu into del u del y, that means mu del 2u del y plus del 2v del y del x, right? Because there is a, it will be del del y of del v del x. So this can be written like this, right? And for the last term, del zx, it will be mu del 2u del z2 and del z of del w del x. So it will be plus mu, here there will be mu, del 2w del z2 plus mu del 2w, del 2u, right? This is u, right? So this is del 2u del z2 del 2w. Okay, so this is u. This is u and del 2w del z del x, right? So this is the expression. Now if you combine this, what will come? So minus del p del x, okay? And if you take common one mu, so from this term one del 2u del x2 plus from this, so from here we are dividing, we are taking one term, we are taking this term, mu already there, so it will be del 2u del y2, and from this last term it will be del 2u del z2, right? Plus again there is a mu and you can take common del x, so it will coming as mu into del x of, so del u del x plus from this term it will be del v del y plus from this term it will be del w del z, right? Now again in this case, so we already know that if you close very carefully, we know that this term, if you remember, this term is nothing but your continuity equation, right? Or this is nothing but the divergence of V equals to 0. As we are already taking it as incompressible fluid, so we can easily take this term as 0, right? So this term will be 0 in case of incompressible fluid. Okay. So now what is left? We are left with the rest of the terms. So now if we go back and put this term, put this expression in the Navier-Stokes equations, in the x component of Navier-Stokes equation, that is this. So now we have the expression for this term, right? This whole term. So now if we go back and put this, what will come? It will come in the left hand side, it is already as it is. So for x directional, it is the rho del u del t plus u del x plus v del u del y plus w del u del z equals to, so this trace term now you can write this expression minus del p del x, right? Minus del p del x plus this term is mu into del 2u del x square plus del 2u del y square plus del 2u del z square. So it is del 2u del x square plus del 2u del y square plus del 2u del z square, right? And there is another term which is a body force term, that is the rho gx, right? So this is the x component, detailed x component momentum equation of Newtonian and incompressible fluid. So the previous equation, this is that was the generalized form, right? As we are taking it as Newtonian fluid, so this symmetric tensor concept will come, and this will simplify like this, right? Next, y component, if you write similarly, it will be rho del v del t plus u del v del x plus v del v del y plus w del v del z equals to minus del p del y plus mu del 2v del x2 plus del 2v del y2 plus del 2v del z2 plus rho gy. Next, for the z directional, similarly, it is coming as rho del w del t plus u del w del x plus v del w del y plus w del w del z equals to minus del p del z plus mu into del 2 w del x2 plus del 2 w del y2 del 2 w del z2 plus rho gz, right? So if you summing it all up in the vector form, what will it be? It is we have already written like this: rho capital dv dt, right, equals to rho del v del t plus v dot or divergence grad v equals to minus grad of p, right, plus mu divergence square of v plus rho g, right? So this is the Navier-Stokes equations for incompressible and non-Newtonian fluid. This is the basic equation and you can use it anywhere for you solving the equations, right? So what does this term, this left hand side term, so this left hand side term talks about the local acceleration. So local acceleration plus convective acceleration into density. So it talks about the inertial term of an phenomena. So this talks about the inertial term. Okay, this is your viscous term because viscosity is related. So this is the viscous term, and these two combines the dissipation term or generation term. So generation or dissipation term, okay, which includes the body force. Okay, so these are the terms of Navier-Stokes equation. So if there is no viscous term, so what will be? The equation will change like rho into dv dt total acceleration equals to rho g or equals to minus grad p plus rho g, right? There is no viscous term. So this equation is called Euler equation. Okay, this equation is called Euler equation. Okay, so now there are different definition or problem along with it, which already have been taught in details in the lecture. So I'm not again going through it. There are different equations, how the equations are applied, and that. So you have already seen the cylinder. So this is the Cartesian from Navier-Stokes equations, right? So this is the Cartesian from Navier-Stokes equations in the x, y, and z direction coordinates. So this equation can be changed into the cylindrical coordinate or spherical coordinate, which you have seen already. And there is a book, BSL, Burt Stewart Lightfoot Book of Fluid Mechanics, which have transport phenomena, sorry, which have which have like everything is there related to fluid, and that is a very good book. You should go through that book to know the terms. Okay, so in the lecture only the tilted fluid of a falling film, or tilted fluid, then the rotational fluid, these derivations, considering the Navier-Stokes equations has been done, and there have come some already defined equations which are very famous, and using that equations we'll be solving questions. Okay, so now I'll first discuss the questions, and if time permits, then I will again come back to the equations or derivations. Okay, so next. So an ideal fluid is defined as the fluid which is compressible, incompressible and non-viscous, has a negligible surface tension. So an ideal fluid is incompressible and non-viscous, right? We have seen that because it is an ideal fluid, so no fluid is incompressible and non-viscous. Every fluid has some compressibility and some viscosity, but we are taking it an incompressible fluid for easy calculation. Okay. Next, the fluid forces considered in the Navier-Stokes equations are pressure, viscous, and turbulent. Body pressure and viscous, body pressure and turbulent, body viscous and turbulent. So what are the Navier-Stokes components? So we have just seen there is a gradient of pressure term, right? So there is pressure. Okay, there is pressure. There is a body force term which is defined by the rho g expression, and there is a viscous term, right, which is defined. So just now we have seen what is the components of Navier-Stokes equation. So this is option B. Next, Navier-Stokes equation describes the motion of solid substance, non-viscous fluid, viscous fluid, or gas. So Navier-Stokes equation specifically account for the viscosity of fluid, right? So it is the viscous fluid. It describes the motion of viscous fluid. For non-viscous fluid, we have just seen it is the Euler equation. Next, in the Navier-Stokes equation, the convective acceleration in the inertial term is linear, non-linear, negligible, or none. So this Navier-Stokes equation is a partial differential equation. Non-linear. This is also non-linear. This is partial differential equation. So for that we have to see a lecture. So I will add those slides in this case in this material of this week. But let me first find it. Just a minute. So how these non-linear linear terms are coming, I will show. So basically, so you have seen the Navier-Stokes term, right? So which is the convective acceleration term it is asking about, right? So convective acceleration term is v into uv. So which term is non-linear? So when we can say something is non-linear? So when a dependent variable is in multiplication with another dependent variable or the same dependent variable, right? So in this convective acceleration term is represented as u del u del x, suppose, or u v del u del y, right? So u are the, so we are finding, so u are the dependent variables. So independent here, independent variables are, so here independent variables are u, sorry, x, y, z and t, right? That means position and time. So these are together, they are called spatiotemporal. So this is together, they are called spatiotemporal. So these four are the independent equations, right? Independent variables, sorry. And what are dependent variables? So we need to find dependent variables. So dependent variables are u, the velocity components u, v, w and pressure. Okay, so these are the dependent variables. So when one dependent variable is in multiplication with another dependent variable or same dependent variable or gradient of that variable, these terms are called non-linear terms. So this convective acceleration in the inertial term is the non-linear term. Okay, I'll show you later what I am trying to show. First, complete the equation part or problem solving part. Next, a low value of Reynolds number means that which one is large in comparison with this one. So how this Reynolds number is coming? So you have seen the expression, right, of Navier-Stokes. Suppose we are only considering the x component. So what was the x component? It is rho del u del t plus u del u del x plus v del u del y plus w del u del z equals to minus grad p plus divergence of mu into del 2u del x2 plus del 2u del y2 plus del 2u del z2 plus rho g, right? So this is your inertial part, and in the right hand side it comes the viscous part, right? So in the from the Reynolds number definition, what do we know? It is the ratio of inertial forces by viscous force, right? So it is said a low value of Reynolds number means inertial force is low. So viscous force will be dominant here, right? So viscous force will be are large in comparison with inertial force. This is option C, right? So now you can visualize it, that how this is coming. Next, consider a fluid is flowing between two stationary plates. The velocity near the plate will be equal to what? So there are two plates, right? And fluid is flowing like this, right? Two stationary plates. Plates are not moving. The velocity near the plate will be 0. Why? Because this is the no slip condition. This is the no slip condition. In the no slip condition, what we assume? We assume that the relative motion of the fluid and the adjacent wall of the fluid is 0. That means at this portion, the fluid, the relative motion between this and adjacent fluid, adjacent wall is 0. Okay, because the plates are stationary here. If the plates are moving, then this no slip condition will not be valid. Okay, so this is 0. Next, consider the balance of forces acting on the respective faces of an assumed small volume dx dy of unit width. So here unit width means dz is unit. So like dz is 1 unit. Value of dz is 1. So that is why it is called it unit width. In a fluid as shown in figure. Now the equation for the velocity distribution is given, which is a parabolic equation. Like you have also derived it in the first lecture. Okay, derive it for yourself also. Okay, because you will be given an unknown system in your exam and you have to derive it for your own, which term for you from your understanding of the fluid motion, whether body force term is important or not, you have to calculate that. You have to understand, and for that case, whatever examples are given in the lecture or in the different books of McCabe Smith and Burt Stewart Lightfoot or any other fluid mechanics, fluid dynamics book, please go through that, and not only go through that, please solve by your own, because like unless you solve it by your own without looking at the problems, without looking at the solution, you won't be able to solve it by your own at later stage or at your exam. It is very important to solve. by your own. Okay, not just copy and paste it. Okay, and not just go through it like from by looking at the equations you may be understand by you are not internalizing it, right? Because unless you do it in a copy and pen with a copy pen, and if you don't scratch it, right, it will not internalize. Okay, so please go through and please do it on paper. Okay, and solve by your own, and you can find if this same equation is coming or not. Okay, whatever the solution is given. Okay, okay, let's get back. And so which is a parabolic equation. To obtain the maximum velocity, y can be replaced as h by 2 and du dy will be 0. Based on the given errors, find out the mean velocity. So you have no, so this is a plate, right? So velocity curve will be like this, like velocity profile will be like this, right? So there will be in the boundary, there will be the boundary layer effect, viscous effect, friction effect. So the flow will be at the middle, the flow will be maximum, the velocity of the flow will be maximum. So if u is given like this, so we'll replace y with h by 2. So what will be that? U max will be minus 1 by 2 mu dp dx h minus h by 2 into h by 2, right? So what is coming? U max minus 1 by 2 mu dp dx this will be h square. So h by 2, this will be h by 2. So h by 2 into h by 2 is square by 4, right? So this is coming as minus 1 or h square by 8 mu dp dx, right? Now what is q? So u means the volumetric flow rate divided by its area. Its area. Just a minute. So volumetric flow rate by area, right? By area. This is your like mean velocity. So how q is defined? So q is integration from 0 to h, integration from 0 to h u W dy, right? So it will be integrated from 0 to h. As width is W is 1, we have seen that width is 1, so we are ignoring it. So it will be U into dy. U is given like minus 1 by 2 mu dp dx h minus y into dy. So if you do the integration, what it will come? So it will be q into minus dp dx and 1 by 2 mu will be there. 1 by 2 mu will be there, and it will be h hy dy, right? It will be hy dy, that means h by there is h square. Is there? Okay. So it will be h by 2 y, h into y square by 2 minus that there will be y square, that means minus y cube by 3, minus y cube by 3, and it will be integrated from 0 to h, right? So it will be coming as minus del dp dx 1 by 2 mu. So h by square means, so this is h cube by 2 minus h cube by 3. So 0, there will be no term left. So it will be 2 to 3, 6, 3h cube minus 2h cube. So it will be like minus dp dx. It will be h cube by 6 into 2, 12 mu, right? This is the q expression. Now u mean is, we have seen u mean is q by a, right? So this q is this and a is the area, right? A is this area. So that will be q by area is w into h. W is the width. So we have known that w is unity. So we will be ignoring that. So it is nothing but the q by h. So it will be minus dp dx h square by 12 mu. So this is your u mean, and u max is coming as minus dp dx h square by 8 mu. So u mean will be, so if you do u mean by u max, so minus dp dx will be cancel out, h square will be cancel out, and it will be 8 mu by 12 mu. So it will be 8 by 12. That is 2.3, and it is coming as 0.67. So the answer will be, u mean will be 0.67 u max. So this is C. Next question. For the laminar flow of a fluid in a circular pipe of the radius r, the Hagen-Poiseuille equation predicts the volumetric flow rate to be proportional to. So, how this Hagen-Poiseuille equation will come? If you have seen already in the lecture. right? So now I'll directly write the expression of Hagen-Poiseuille equation. So here Hagen-Poiseuille equation in a circular pipe, Q equals to pi d to the power 4 delta P by 128 mu L, right? So d to the power 4 means diameter to the power 4. So for radius also it will be 4, right? So it is the option D. Volumetric flow rate will be proportional to the fourth order of radius. Next. In turbulent flow, the average velocity is what of maximum velocity? So you have seen, suppose in a flat plate, if this is the turbulent flow profile, so this will be the, I have drawn it very bad, so just bear with me. So this is, it will be little bit curved and this will be lit straight, and this is the profile. So this is the turbulent profile and this red one is the laminar flow profile. Okay. So in case of laminar flow, it is the half or 0.67 of the maximum velocity, the average velocity. So for in case of turbulent flow, it is the it is more than 0.5 and up to 0.85. Okay. Next, the turbulent eddy viscosity varies with pressure, temperature, pH of fluid and flow condition. So eddy viscosity will obviously depend on the flow conditions. Okay. So it is option D. Next, mixing length depends on the velocity gradient, distance from the wall, both of A and B, and none of the above. So mixing length depends on both A and B, that is the velocity gradient and the distance from the wall. So if you remember the mixing length, like here comes so if you see the boundary layer lecture, so you can see here. I think you will not be able to see. Just a minute. So here you can see the mixing length. So what it is written that Prandtl's mixing length theory is based on the concept of momentum exchange between layers of fluid in turbulent flow. So you can see that when the fluid is passing through an object, and after passing through an object, the fluid layers mixes with each other. So this length is called the mixing length. Prandtl correlate the fluctuating velocity in the turbulent flow by considering the assimilation or mixing of a rotating parcel of fluid of turbulent flow with the character of the other fluid parcels by collision with them. These parcels are called eddies, like this. These are the eddies. The pattern they are created is called eddies. During the assimilation, the average length traveled by the eddies is called the mixing length. Okay, so how these eddies are moving, then what is the average length of these eddies is the mixing length. What was the question? The question was mixing length depends on the velocity gradient or distance from the wall. So it is obviously depend on the both of the things, right? It is a velocity gradient and distance from the wall both. So option C. Next, the Reynolds number will be maximum in the case of A, B, and C. So you know already that this is the laminar profile. C is the turbulent profile and B is in between them. So obviously the Reynolds number will be maximum in case of C. Next, for 2D flow, the instantaneous velocity of fluid particles is in the turbulent flow condition is expressed as this. Here U bar represents the average mean velocity, maximum velocity, overshoot velocity, or fluctuating velocity. So this is the fluctuating velocity, right? Because U bar is the average velocity, average mean velocity, and U bar is the fluctuating velocity. Suppose there is a flow and this is the mean velocity U bar, and now the turbulence, when the turbulence happens, fluid particle, so this flow patterning will change like this. So this turbulence is called the fluctuating velocity, U bar, U dash, or U prime. Next, the thickness of a boundary layer with the distance from the leading edge with increasing the free surface velocity. So what is boundary layer? So basically it is the it is the effect of the boundary. So suppose the fluid is flowing, and till when the fluid is achieving the 0.99% of its maximum velocity is called the boundary, that is the boundary layer thickness, right? So exact definition is like this. So suppose at this point, suppose I am drawing. So when the fluid flow is starting, so this is the, suppose this is a flat plate and fluid is moving. So here this is U velocity, this is going. So you can see the effect of boundary here. So this portion of the fluid velocity is not achieving the fully developed velocity, right? And after some point, after some point this will increase, and just this is the level of fully developed portion. So this distance from here to here, how the boundary is boundary of this, like how this plate is obstructing the flow layers or velocity of every fluid layer is described by this boundary layer theory. So at this case, after this point, it has achieved the fully developed condition. And in this case, after this much portion, these fluid particles have achieved the fully developed condition. So what it is said. So suppose this is x direction and this is y direction. So here x equals to x1 zone and here x equals to x2 zone, right? So what it is written that the thickness of the boundary layer increases with the distance. So here it is increasing with the distance x from the leading edge. So as the x is progressing, the boundary layer thickness will also increase with with decrease and decreases with free surface velocity. So the thickness of the boundary layer increases with the distance from x, as you can see from here, and decreases with the increasing free surface velocity. So as the velocity is increasing, the thickness of the boundary layer is decreasing. Okay, so it is the option C. So if the velocity of this, like free surface velocity, will increase, this boundary layer thickness will decrease. This boundary layer thickness will decrease, but it will obviously there and it will obviously increasing with x, but the higher free surface velocity it will decrease, right? Next, the local drag coefficient is proportional to what? So you have seen in the lecture the local drag coefficient CF is proportional to 1 by root under RE x. So that is RE to the power minus 0.5. Next, select the correct equation for the linear velocity profile where u is the velocity, capital U is the local velocity and delta is the displacement thickness. So for linear velocity profile, obviously u by u will be y by delta, right? Because if you notice the other cases, it is giving a like parabolic kind of equations, right? Next, in the laminar boundary layer flow over a flat plate, the ratio delta by x varies as where delta is boundary layer thickness and x is the distance from the leading edge in the direction of flow. Delta by x varies or is proportional to delta by x is proportional to 1 by root under REx. So it is again RE to the power minus 0.5. Next, lubricant is used to lower the viscosity, to increase the viscosity, to generate the foam, to none of the above. Obviously, lubricant is used to lower the viscosity. So lubricants are used because to reduce the friction between two moving parts in case of equipments or joints or any cases. So its work is to lower the viscosity to make it more smooth. Next, which is not the property of a good lubricant? Should adhere to the surface and reduce the wear, should possess good heat transfer capabilities, should have oxidative stability, should have foaming ability. So which is not the property of good lubricant is the should have foaming ability. So it should not create foam. Otherwise the point of lubrication will be finished. Next, a shaft rotates centrally in which type of bearing? A shaft rotates, if you go through the shaft portion, you will find that the shaft rotates centrally in case of bush bearing. If you find the lecture, so here it is there, I think, the last lecture. So there are different types of bearings they are talking about. So bearings are machine elements which are used to support a rotating member or a shaft. So there are three types of bearings based on type of load carried: radial bearing, thrust or axial bearing. Then comes the lubrication type: thick film, thin film, boundary lubrication bearing, and based on lubrication mechanism. So here you can see this is the different type of bearing. Okay. Next comes different questions. Some more question like the derivation of the Navier-Stokes equation. What does the term rho du dt physically mean? What does this mean? So rho du dt term is the inertial portion, right? Right. So it is the inertial portion, right? So this is the we have just seen the left hand side of this Navier-Stokes equation is the inertial force per unit volume. So this is C. Next, for laminar flow between two parallel fixed plates, the ratio of maximum velocity max to mean is 1.5. So if you go through the lecture of fixed parallel plates and their flow, you will find this. Okay, I'm not doing the derivation again because it is already in the uh, lecture notes. Which of the following is not a property of good lubricant? So a high thermal and oxidative stability, compatibility with steel materials, ability to produce significant foam to reduce friction, adhesion to the surface to reduce wear. So it all definitely have definitely has to have anti-foaming capability. So option C is the correct option here. Next, The displacement thickness delta D in boundary layer theory is defined as the distance where the velocity is 99% of the free stream velocity. The distance by which a surface would have to be moved to maintain the same mass flow rate as an ideal fluid. The thickness where turbulent mixing is suppressed. The distance where the velocity gradient is maximum. So the distance where velocity is 99% of the free stream velocity is the boundary layer thickness, but displacement thickness is option B, where it has to be moved, the distance it has to be moved to maintain the original or ideal fluid, maintain the same mass flow rate as an ideal fluid, option B. Next, according to Prandtl's mixing length theory, the Reynolds stress in turbulent flow is proportional to in the Prandtl theory, the Reynolds stress is proportional to rho L square tau T equals to rho L square du dy square. So it is option B. Next, a fluid with viscosity mu flows through a circular pipe of diameter d and length L. If the mean velocity of this is calculate the pressure drop across the case. So from Hagen-Poiseuille equation, right? From the Hagen-Poiseuille equation, we can calculate the pressure and volumetric flow rate in a circular pipe. So pressure drop equation is given as delta P 32 mu L U mean divided by T square. So 32 into 0.05 into 10 into 0.2 divided by 0.1 square. How much it is coming? So it is coming as by 0.1 square. It is coming as 320, right? So the pressure difference is across the pipe is 320 Pascal. If you want to remember the equation, please practice it. Otherwise, you have to derive it from the whole starting Navier-Stokes equations, which is difficult in a case of like exam. Next, assuming a linear velocity distribution within a boundary layer of thickness delta such that u by u infinity equals to y by delta, calculate the displacement thickness. So, from the definition, displacement thickness is defined as delta D equals to integration from 0 to infinity 1 by u minus u infinity into dy. Okay, so it will be 0 to infinity 1 minus y by delta dy equals to y minus y square by 2 delta 0 to infinity. It is coming as sorry 0 to delta. It is the boundary layer thickness. So it is delta minus delta square by 2 delta. It is delta by 2. So this is the answer. Next, a slipper bearing has a lubricant of viscosity 0.02 Newton second per meter square. Okay. Now the bearing plate moves at V. The gap reduces from H1 to H2 over a length L. Calculate the location where maximum pressure occurs. So from the derivation you can see in the lectures this maximum pressure X is given as LH1 by H1 plus H2. So if you put the values you will get it. So it is 0.2 into 0.08. So this is not in millimeter, this is meter. Okay, this is meter. Divided by 0.08 plus 0.04 equals to 0.133 meter. Okay. Next, which term in the Navier-Stokes equation is responsible for non-linearity of the equation? So we have done it in the first question, first couple of questions. It is written there that the convective acceleration term is the non-linear term, right? This is option B. Next, in the universal velocity distribution for turbulent flow, the buffer layer exists in which range of y plus? So it is option B. It is in the between 5 and 30. Next, the drag coefficient CD for a laminar boundary layer over a flat plate is proportional to Rx to the power minus half. So it is option B. Next, what happens to the boundary layer thickness as the fluid moves further downstream along a flat plate? So boundary layer thickness will increase. Okay, so we have seen that. Next, water flows through a pipe of diameter d. The velocity distribution is given as the power law. If the maximum velocity at the center is 2 meter per second and the density of water is this, calculate the mean velocity. So mean velocity expression is given. So if you calculate is as mean velocity v, or u mean you can also write. So it is u mean by u max equals to 2n square by n plus 1 into 2n plus 1. So from the turbulent boundary velocity distribution, you know that n is 7. It is given like this 7. So it will coming as u mean to 2 into 2 into 7 square by 7 plus 1 8 into 7 into 2, 14 plus 1, 15. So it will be 2 to 4 in this is 2. This will be 7 square by 2 into 15. 49 by 30. It is coming as 1.633 meter per second. 1.633 meter per second. Next, given a boundary layer velocity profile, this calculate the momentum thickness. So, momentum thickness definition is given as theta equals to 0 to delta u by u infinity into 1 minus u by u infinity into dy. So, it will be 0 to delta. So, you can represent y by delta as eta. So, dy will be delta d eta. So 0 to delta it will be 2 eta minus eta square into 1 minus 2 eta minus 1 say plus eta square into this delta will be coming out and it will be d eta equals to, if you simplify, if you remember the integration, so if we expand it will happen like this, like delta in integration from 0 to delta, so it is like 2 eta minus 4 eta square plus 2 eta cube minus eta square plus 2 eta cube minus eta to the power 4 into d eta. So now if you summarize what it will come, it will come theta as delta into 0 from 0 to 1. So it will be obviously 1, sorry, I have forgotten to write. It will be, because we are classifying it as in the term of, so we're classifying it in the range of from y range it is transferring to eta range, right? So y by delta and eta. So when y equals to 0, it will be 0, and when it will be y equals to delta, it will be 1. If you remember the class 12 integration, right? So 0 to 1, it will be 2 eta minus 5 eta square plus 4 eta cube minus eta to the power 4 d eta. Okay, so if you remember, so I'm just directly multiplying delta into 2 eta, like 2 by 2 eta square, so it will be eta square minus 5 by 3 eta cube plus 4 by 4 eta to the power 4 minus 1 by 5 eta to the power 5. It will be from 0 to 1. 0 to 1. So if you take another, what is coming? So it is coming as theta equals to delta into 1 minus 5 by 3 plus 1 minus 1 by 5. So it is the delta into 2 minus 15, 25 plus 3. So it is delta into 15 into like 30 minus 28. It is 2 by 15 into delta. So this is your answer, momentum thickness. Last question from this session, like if a journal bearing or bush bearing, in a journal bearing or bush bearing, the film thickness is maintained by a lubricant with viscosity mu, and if the pressure distribution P theta is known, how is the total load will W calculated? So the total load will be the integral of the pressure component over the bearing surface. So for vertical or horizontal component, there are two components. So vertical component Wx will be integration of P sine theta r d theta L, which is the area, and this will be P Wy, that is the vertical and horizontal. P cos theta r d theta L, and total W will be the summation of Wx square and plus Wy square. So this is the answer. Okay. So one thing I want to show, that is, let me find this thing first. So I am showing the terms, each terms of Navier-Stokes equation, how these things will come and express. So it is a little bit big PPT, so that is why it is taking time to open. Just bear with me. So, so here this is the Reynolds transport theorem. Okay. So you can see the conservation of mass, conservation of momentum, and this is doing the summation. Okay. So this is the conservation of momentum. So this is the surface forces which we have talked about, right? So this diagonal component of tau xx, tau yy, and tau zz are called the normal stress, are due to pressure and viscous stresses. And off diagonal components are all these off diagonal components are called shear stresses and are due to solely the viscous stresses. Okay. So here you can see. So this is the body force term, and these are the surface term. And these surface forces includes all other pressure forces, viscous forces, and all other forces. And you can see this is the you can see the stress term. So you have seen that, like tau xx, tau yy, and tau zz has a pressure term, right? Extra pressure term. So this pressure forces, which is the surface forces, right? So this extra pressure term, like if you represent this stress term in the way of this tensor, so this is the one tensor, stress tensor, and this is its P component, right? So what will happen? So now this P component is called the pressure, and this is the viscous stress system, right? So this is the principal stress, and this is the pressure tensor, and this is the viscous stress tensor or the deviatoric stress. It is called the deviatoric stress. Yeah, because yes. So in the Navier-Stokes equations, in the stress tensor, you will find that there are 6 independent components. Why 6? Because we have we have symmetrically we have considered this is a symmetric tensor, so these 6 terms has reduced to 3 terms, and the other 3 diagonal terms. So there are six tensor terms. There is density, which is unknown. There are 3 velocity components, which are also unknown. So 6 plus 3 plus 1. So that is a 10 unknowns. And what for 10 unknowns, we need to have 10 equations, right? But we have 4 equations, right? We have 4 equations. So one is the continuity equation, and another 3 are the momentum equations. So that is why Navier-Stokes equations in its correct form, or in its original form, it is not solvable, because we have to reduce the number of dependent variables, right? So that's why the symmetric that's why. So now here the six unknowns are there, and another unknown is included, which is the pressure term. So it is again 7. Okay, so the situation is still same. Then how will you solve? Because you cannot solve Navier-Stokes equations in its original form, and because of that, because you want to get some analytical solution or some idea of how the flow is happening, or how the equation is working, so you have to take lots of assumption to that, and that is how these expressions are come. This is the generalized form of Newton's law of viscosity. Okay, so this is how it is coming. Okay, so this is the final Navier-Stokes equations, and now you can see there are 4 equations, and finally, as you have expressed all these stress terms clearly, and so now you have 4 unknowns, which already I have discussed that what are these are dependent variables, 3 component velocities, u, v, w, and p is the pressure. Okay, so this is the Navier-Stokes equation in the incompressible form, or Newtonian fluid, for a Newtonian fluid. So this is the second order nonlinear coupled partial differential equation. Why nonlinear? Because you can see that the dependent variable is in multiplication of the gradient of the dependent variable. That's why this convective acceleration term is the nonlinear term. Second order because second order in space and first order in time, right? So second order in space means because it has second order del u, del 2u, del x2. So that is the second order in space, and first order in time, because in time, with respect to time, only one derivative is there. One order derivative is there, so it is the second order non-linear coupled partial differential equations. So all these equations are coupled. So I have said that why this is called Navier-Stokes equations, because if it is equation, then we have to solve one, because with one equation you cannot solve anything for a fluid component. So for solving Navier-Stokes equations in its simplest form, you have to use all these equations. That is why it is called the coupled partial differential equation. I hope you have understood this. So we'll change these forms to ODE. So this is the generalized form of two-dimensional PDE, right? So when this b square minus 4ac greater than 0, it is called the hyperbolic part. B square minus 4ac equals to 0, when it is the parabolic part, and b square minus 4ac less than 0 is the elliptic part, right? So if a, b and c, this a, b and c is a function of x and y, this is called the linear term. If they are function of phi, then this is the non-linear term. So from this case, you can understand how it is changing. So this portion of the, like this is the viscous portion of the, if you compare this term with the Navier-Stokes equation, if you remember, the Navier-Stokes equation has del 2u del x2 plus del 2u del y2 terms, right? So this is the viscous term. So viscous portion is your elliptic portion. Okay, so viscous portion is comparable to the elliptic portion. That means b square minus 4ac is b square minus 4ac is less than 0 there. Okay, so this is the, so though the viscous portion is comparable to the elliptic portion, and when these terms are there, this is these terms are there, right? So when only viscous flow is there, suppose del 2u del 2 del 2u del x2, if you remember the Navier-Stokes equations here. So if I refer it, so when we are solving Navier-Stokes equations here or here, suppose suppose every other term is 0. Okay, suppose inertial term is 0, there is no pressure gradient, there is no body force, only this term is present, right? Only this term is present, then it is called the elliptic flow. Only the viscous flow is there, and that is called, I think, the, it is written that steady state laminar flow, it is the Poisson's equations. Next, when there is only this part and the total acceleration part is there. So here in this Navier-Stokes equation, only this term is there, only the left term, only this term, okay, del u del t term, time dependent term, and this right side term is there. That means convective acceleration term is not present there. So when these two term only present, so this, that is the parabolic form of Navier-Stokes equation. So that is the parabolic form of Navier-Stokes equation. Okay, so, and now where b square minus 4ac equals to 0. Okay, and when hyperbolic terms are present, like if we have in linear like in Navier-Stokes equations, we don't have like second order of time dependent property, so we are not able to consider it here. But if there is something like this, then that will be b square minus 4ac will be greater than 0, and it will be hyperbolic problem. So our Navier-Stokes equation is have two forms, like elliptic forms and the parabolic forms. Okay, so you can see here, right? Okay, so this is just to compare it. This I have just shown this part just to compare it with like how the nonlinear terms are there and how this is called second order coupled equations. So if I write it, if you remember, it is the first order in time and second order in space nonlinear coupled partial differential equations. Okay, to solve it we have to do ordinary differential equations, and we are as in the original form of Navier-Stokes, you can see that there are more unknowns than the equations, so we have to express these unknowns, this stress term in normal pressure and the deviatoric stress term or viscous stress term, and that will lead to the four unknown, which is u, v, w, and p, and four equations. So that is how we can convert partial differential equations in ordinary differential equation form, and we can solve it for various systems in fluid flow. Okay, so I think you have a little bit understood what Navier-Stokes equation is, how this is the fundamental equations for fluid flow operations, uh, fundamental equation of fluid flow operations, and how you need to uh, like derive it or need to solve this equation every time if you want to solve something in viscous fluid, right? So please go through the lecture well, and like in the CERN notes, many things is there. Then for pipe flow, for quid flow, for falling field, for cylindrical flow, how these equations are changing. The basic equation is same everywhere. The terms are different, like final form is different, but the starting point is same in everywhere. And please go through these things so that you can solve it by your own. And I hope you will understand something from this lecture, from today's discussion. And we'll meet in the next week with the next part. Till then, goodbye.